Today we are going to start SVM, but this time I have decided not to focus too much on SVM. Instead, devote a bit more time on other concepts. Probably we will dedicate that time onto the a little more newer techniques in the decision trees, but it is important to know the SVM, and it's important to know that they work pretty well till some point, and then the other techniques took over. All right. So so this is that's the important part. We will go into um, support vector machines now. And all right. So remember how the general flow of machine learning problems look like. We divide the data set, train the model using training data set, test using sample training data, and then we check the performance metrics, finalize the model, improve the model using the analysis. So there can be several models depending on the problem statement, and we will discuss one such model called SVM, right? So basically the training part is, instead of using the linear regression, instead of drawing a straight line through the data, will be using SVM. Instead of using gradient descent, SVM uses a mathematical equation to come up with the value. Just like remember the one that we talked about in the normal equation, that one is a mathematical formulation, like optimization technique. Without any much of a iteration, the SVM actually get solves those optimization problems, right? So support vector machine is a very powerful and versatile model capable of performing linear and nonlinear classification, regression, and outlier detection. It is well suited for small or medium-sized datasets. In this session, we will learn about linear SVM classification, nonlinear SVM classification, and SVM regression, right? So first of all, we will start with the SVM classification. And essentially, it's a classification is a part of supervised machine learning, right? Now, like examples of classification is when we are trying to identify an image. When we are trying to label an image, whether it's 5 or not 5, that's a classification. So classifying image as spam or not spam. So it's essentially a binary classification, correct? So similarly, classifying flowers of a particular species like iris data set is, what type of classification is this? That's right. So it's basically the multi-class classification, right? All right, great. I'm going to move a bit faster in case you have questions. Please feel free to stop me. And classifying credit card transaction as fraudulent and not is again a classification. Similarly, we talked about the face recognition one. What type of classification is this? Quickly. Single instance to be labeled with multiple persons, right? Yes. Yes, it is multi-class, but as well as it has multiple columns, which are targets or which are labels. Okay, so it's called multiple label classification because there are multiple columns of target. Like we are saying that in this image there are three person one, person two, person three. All right, that's yeah. Now, what is classify we used for the binary classification? We did a test last time, and we were doing the binary classification. We used a particular classifier. That's right. We used the SGD classifier. Logistic, yes. Logistic is essentially the one that is there when we are converting a problem into logistic. Essentially, logistic classification logistic classifier basically is a part of defining the objective function. But the overall, we were using the SGD for that. All right, that's right. Great. And what is the classifier we used for multi-class? We did use something for multi-class. Okay, so we used SGD. What all we did was OVO and OVA. One versus all and one versus one. One versus one is generally rare. One versus all is what people use. All right, great. Moving ahead. So what is the linear classification? Okay, linear classification was this, right? Now, this is a very important part, so we're going to talk about it. So the two class can be separated easily with the straight line, right? There are blue ones and there are the the blue ones representing versicolor and the other ones representing setosa, right? So here the important part is that we are able to separate these two classes. So let's say we took the various instances. Let me describe what is the meaning of this one. We took various instances, and what we did was we drew petal length and petal width, right? We drew petal length and we drew petal width on X and Y axis, and we got this kind of instances, right? This ones are versicolor, this ones are setosa. Now, this can be separated easily with many kind of lines. This data can be separated easily with many kind of lines. Now, you see that there are three kind of lines we have drawn: one, two, and three, right? So, which one out of these three lines you don't think that is right one? The green, right? The dashed one is not really a classifier, correct? So here we are able to do the linear classification essentially means that we are separating the data using the straight line. Yeah, so linear classification essentially means that using a straight line, we are able to clearly mark the difference between the two classes, right? This is one such model, this is another such model, and this is third model, which doesn't seem to work at all, right? So, which seems to be wrong, okay? Seems to be wrong. And if we have to name it, we are forced to tell this one as underfitting or overfitting. What will you tell? This one? If I ask you that this is, we have to either tell underfitting or overfitting without any third option. What will you label it? Underfitting. That's right. Model is wrong or not performing, so we politely tell in such cases that it is underfitting. Good point. All right, great. And all of you just keep chatting or keep responding. That way, you or we all stay in the same context. All right, and great. And in case you are logged in from the tablet, I would strongly suggest that come over to either not tablet. In case you're logged in from any devices where you can't type comfortably, come over to some device. All right, and great. And here the state is the keyword and it means linear classification. Now, like here, what we were doing is we took two features, sepal length and petal length, and there were three classes: Virginica, versicolor, and setosa. These are the three classes which we are trying to separate, right? And if we take a look at them in this sepal length, petal length, and flower type, right? Those are the details. This is the data which we are going to talk about. And if we, okay, just a quick quiz and just to keep all of you in the context. So let's say here we are going to take an example of the iris dataset. whereby we're going to take two features, sepal length and petal length. And there are three classes, Virginica, Versicolor, and Setosa. This is how the data looks like, right? For this length, this, so this is basically the flower types which we are trying to identify based on these two parameters, so two features. And the last one is your target, and these are your features. So question is, for the above iris data set, what type of machine learning model, classification or regression? It's like just a very, very simple thing. Just feel free to type just to keep everyone awake and engaged, right? Yes, it's a classification. That's right. Great. Thank you, Robert. Now, what type of classification it is? Yes, that's right. It is multi-class classification. Perfect, perfect. And now for the iris data set, the one that we are taking right now, the one example that we're taking right now, how many features are we taking right now? Two. And number of classes, three. That's perfect. Thank you. So we are taking two features and the three classes, and versicolor, setosa, and virginica. All right. Now, when we plot the two features on the graph and label it by color, the classes can be divided by a straight line. Hence, we call it linear classification. And you can see that these are the straight line that we are trying to draw. Now, first, what we are going to understand in case of SVM is we are going to understand what it means by a good model and bad model, right? So this is the only important part I found about SVM that we need to learn. Now, here, pink and red decision boundaries are very close to the instances. All right, now let me ask you this question. So all right, let me take a screenshot of this one and move ahead. And I want to discuss this part. Okay, so probably all of you know this already. So I'll just jump into it ahead. Okay. Question from Robert is, with two features, you get two thetas. That's right, theta zero. You get actually three thetas. One is the bias, theta zero, theta one, and theta two, right? In case of linear ones. All right, great. Moving ahead. So my question to you is, what kind of line that you would like to draw, right? Which is better? This is better, this is better, or this is better? Or, or let me ask you, this is better. Let's say we call it L1, L2, L3, and L4. Basically, we are given these instances and we have petal width and petal length, right, as two criterias. This guy here, this one has this much petal length and this much petal length and this much petal width, right? This one has this much petal length and this much petal width. So which one do you think, L1, L2, L3, or L4? All right. Okay. Okay. Gonzalo says that L4 is better. Deepak says L1 is better. Now, let me ask you a slightly different question. Let's say there is an instance lying here. What will happen to that? Should that be classified as Setosa, or should that be classified as versicolor? there's an instance lying here which is slightly or maybe the same petal length but little more petal width, right? So this should be, as per your model, should it be um, setosa or should it be versicolor? If you have to yourself decide, look at the length and width and decide, where will you place it? This cross, let's say it here. Yes, Sumit, Satyajit, Robert, Prashant, Nikita, Jay, Gonzalo, Deepak, and Arun. So let's say there's a slightly, this instance, is it setosa or versicolor? Or similarly, let's take another example here. This one, let's call it x1 instance, and this is x2 instance. Okay, so yes, so the x1 and x2 should be setosa or versicolor. Okay, from the visually, what do you think? Do you think x1 belongs to the versicolor, or or it belongs to setosa, right? Versicolor, right? This one belongs to versicolor, and x2 belongs to versicolor or setosa. Same, right? Similarly, if you take this example, let's say here, right? Here. Does this belong to setosa or versicolor? And same case is here. But both these models are, this model and this model, both are wrong in that sense. This model that you see, L1, is telling that the X, this one belongs to setosa. Similarly, this model that you see is telling us that X2 belongs to the X2 belongs to setosa, but these are supposed to be X1 and X2 were supposed to be belonging here, right? Similarly, X3 and X4, this is our X3, then this is our X4. X3 and X4 should belong to setosa, not this. Therefore, this model and this model aren't really great. They aren't really great because they are misclassifying for the unknown data set, the data set that is not known. They are not able to do a great job, right? Is everybody clear about X1 and X2 and X3, X4? Now, as per L4, X1 and X2 both belong to versicolor. X3 and X4 both belong to setosa, right? Yes. So question from Deepak is, but L4 is too far from data points. So here we are not doing the regression. We are doing the classification. We want a boundary. We want a boundary that can break these data sets into two classes. We want a model which can classify these into one class or another, right? So is everybody okay with me? Yes. All right. So, and that's what we are trying to discuss it here. Okay. So there's the state line. So when we plot it, we can divide it using a state line. It's called. All right. So pink and red distant boundaries are very close to the instances, and hence those are bad model, while distant boundary as far away from training instances is a good model. Correct? A question from Deepak is then probability values will be very much near 0 and 1, few around zero point 0.5 for L4. Okay. All right. Let me go back to the point that we are trying to make. Question from Deepak is then probability values will be very much near to 0 and 1, few around zero point 0.5, yes, for L4. Um, yes. Okay. So how should I say? For L4, yes, this is going to be, if we were doing the regression, this is going to be little, how should I say, this is definitely far away from this one. Yes. And that's basically the little bit difference in SVM, that we come up with the line which has the best margin between the data sets, right? So question from Sumit is how X4 being Setosa confirms the model capability, right? X4 is, okay, let me go back here. So here, this model, L1 model, as per L1 model, X4 belongs to this side, right side, correct? Right side of the line. Therefore, X4 will be termed as versicolor, right? As per L1. So as per L1, X1 and X4 are being misclassified, correct? And as per L2, X2, who was supposed to be this, but is being below the line, is being classified as this, right? All right. So as per L1, X1 and X4 are being misclassified. As per L2, X2 and X3 are being classified, while L4 seems to do good job, correct? So instead of fitting a line which is very close to the data points, what we do in case of SVM, is um, we try to figure out a line that has which is at the middle of this wide street. We try to fit a wide street between the data sets. Okay, there could be a little violation, but we try to maximize the widest possible street, and we try to figure out what is that widest possible street that we can fit will have minimum violation and maximum returns. All right, maximum returns. So we try to figure out that street. which we can fit into data points like this, right? What is that widest possible street? Okay, and the distance boundary generally we term it is from the middle of the street. So we figure out as part of SPM, we figured out what is that widest possible street, and the distance boundary generally at the middle of it. Okay, so using geometry, I'll put it this way: using geometry and optimization techniques, we figure out that street that can fit between the two data sets really well, and that becomes our that becomes our the widest possible street becomes our um, the model. Yeah, the distance boundary which is at the middle of the widest possible street becomes the model. Now, a question from Deepak is, since all are getting classified comfortably, I don't know if SVM calculates probabilities for classification. Very good point, Deepak. The quick answer is it doesn't. Okay, it doesn't. We do emulate probabilities based on some things, but it doesn't do that. Good point. Question from Sumit is, how will this make sure that it works good for new data set? Is there any generalized approach? Good, good. So as part of SVM, people figure out that if we come up with street which is kind of having the maximum width. Now there could be minimum maximum such what do you say, such streets possible. So what they figured out was that in case the you draw the line from the extreme points, this and this, you draw the line and draw the widest possible street vertical to it, right? Generally, that is the street. Okay, we'll see that we call it normal. Uh, uh, I mean the orthogonal to this line, and so on. Okay, so is there any generalized approach? Generalized approach here that we are trying to figure out is that if we come up with a street here like this, that'll give us best possible answers. All right, and okay, so going ahead and all right. So the ones that are very close to the instances are not going to work well, that we can clearly see. While the distant boundary, which is far away from training instances, is actually a good model, right? This one, which is basically far away, this is a good model because all the examples that we took here, these very edge cases, they are well classified using L4. Okay, can somebody suggest the instances for which L4 would not work? Anyone? Okay, unseen data, you mean to say, let's say there is something here. Okay, let's say something is here, or let's say go here and here. This is closest to this, and this is right. So even in those extreme cases, you can see we can forgive this model, right? Because if this data point is classified as versicolor and it belongs to setosa, then we can, yeah, I think okay with that. Similarly for this point, it might belong to say versicolor, but it's being classified as setosa, right? We can always call it on the boundary, and we kind of can forgive this model because this seems to be doing okay. right? Because we ourselves are not able to identify because they are on the boundary. Okay, they are on the boundary, and we really can't, we ourselves can't really tell whether this belongs here or this belongs here, right? All right. So, all right. So adding new instances may not perform well on these lines may not perform well, but the one that is there with the decent boundary, right? Adding more data points may not affect the decent boundary, right? In this case, because most of the data points will be there on that side. Now, these lines that you see, the extreme edges of the street are called support vectors. These lines, when we are basically as part of SVM, we come up with this kind of a street, this kind of a street between the two data points, or the lane between the two data points. And these two extreme data points that are lying on the street are called support vectors. These are called support vectors. This is called a street, and this line that you see in the middle is our decision boundary. Okay, this is our decision boundary. As part of model finding, we find the widest possible street. Once we have found the widest possible street, we use decision boundary, the central line, to classify something in one class or another. Okay, just like we had different thing to optimize earlier, and like we had the the regularization term and all those while we were doing coming up with the model. Once we come up with the model, we used something else, correct? So during training, our objective is to figure out this widest possible street, and during prediction we use the distant boundary, not the widest street. Okay, so I hope that clears it. So that's exactly what SVM does. And all right, so basically the without scaling, the training data set looks like this. Okay, and okay, okay, so it looks like this. We have data points like that, and we create a SVM classifier and we fit it. Then we are plotting it and so on, right? So here what we are trying to do is, if we do not do normalization, this is how the data looks like. You can see that the, let's say here it's an unscaled data. There are two features, x0 and x1, and x1 has the x1's values are varying little, very less, while x0 is varying a lot, right? That's how we define the the unscaling, correct? Let's say one's value is varying between 1 to 6, 0 to 6, and other values are varying from 0 to 90. In such cases, since the data points are very uh, skewed, this one is going from 0 to 90, this one is going from 1 to 6, it is hard to come up with a great decent boundary, correct? We generally end up with a tiny thin lane. Okay, so right? So you can see that x0 is varying from 0 to 6, and x1 is varying from from 20 here to 80, right? Therefore, we get this kind of very tiny thin lane because of this, right? Therefore, the one solution that we have is doing the feature scaling. Okay, so feature scaling, a quick revision. I think this you don't need a revision. And basically, there were two kinds of scaling: min max And min-max is basically pulling the initial value to 0 and maximum value to 1 and everything in between, right? So that's what we do. We find the range, we divide the values by the range, and then subtract by the minimum, and so on, right? We first subtract by the minimum and then divide it by the range. All right, that's what we do. Now, min-max sampling is pretty straightforward. You can use the not min-max and not sampling. It's called scaling. Now, right, you can use min-max scaling from pre-processing scikit-learn library. Okay, standardization is good for the cases. Generally, as we discussed, when the data we don't know the data and the data is going to vary a lot, such as audio signals, pixel values from the image data, and so on. In those cases, we use standardization, and standardization is essentially finding how far, how many, how many standard deviation a particular value is away from the mean, how many standard deviation a particular value is away from the mean. That's how we calculate the normal value. So what we do is we first find out the standard deviation, we find out the mean, and we find out the new standard value using this technique. We subtract. We first find out how far is the value from the mean, then figure out how many standard deviations is this distance. Okay, that's what we are doing here. And in standardization, features are rescaled so that output will have the properties of standard normal distribution with zero mean and unit variance. Unit variance. So X, this is the mean, and that's the standard deviation. All right. So after we have converted a value into a normal distribution, the the mean of the new normalized values is 0. Okay, once we have normalized certain data, let's say in your class, if we convert in your class, if we take everybody's marks in the exam and normalize them, the average value of the class, if you are using the normal distribution, average value is going to be 0 because there will be people at the negative, and the standard deviation is going to be most likely 1. Okay, most likely 1, and so on. So I'm not sure. Standard deviation is going to be 1. Okay, it's very hard to prove this part. So the standard deviation of the normalized data is going to be 1. I'm not sure if it is most likely 1 or it's going to be 1. Just think over it. All right. For now, I think I can just note it down, but let me think if we can figure out standard deviation equals 1 for normalized data. Okay, so we did not pay attention to this first. So the standard deviation being 1 is an interesting thing. The mean I can think of because we are making some values negative, we are making some values positive, and the mean is going to be 0. But strictly that the standard deviation being 1 is something that is something that I need to see. All right. Yeah. Mean is 0, yes, and standard deviation. This is basically mean. Yeah. All right. No, this is that one. These are the new values. All right, Deepak, feel free to unmute in case you have. Should it be mean equals 0? Mean would become 0 after we have normalized data. That's what the mean of the normalized data or standardized value becomes 0. Okay, and the standard deviation is 1 for normalized data or standardized normalized, or you can say scaled data. All right. Now, scikit-learn provides us a standard scaler which does the job, and min-max scaling. The range is strictly 0 to 1. Okay. Right, right. So this is very important part. So in min-max, it is guaranteed that the values are going to be 0 and 1, while using the standardization, we are not bound by a specific range, right? Therefore, the data could be having 1, -2, 2, and so on. After standardization, it's not never guaranteed that the data is going to be within 0 and 1. If there is an outlier beyond one standard deviation, right? One standard deviation, then it could be 2. If there's something really spike, or something really deep down, as in if there's some value which is really different from others, in those cases, the standard the standardized value could be -2 or +2 or so. Okay, but what happens is this. Okay, and let me spend a bit of more time. The moment some of the values spike up, the standard deviation spikes up, right? Therefore, this value is not going to be too high. Let's say this x, a particular value is really high. The chances are that the mean is also high, and the standard deviation is also high. Therefore, first this will bring it down, and then this will bring it down. Okay, so therefore this x dash is going to be mostly between say -3 to 3. Within that, I think almost all the values are covered. Okay, try as an exercise to all, try first creating an array and coming up with the standardized value. Now spike up a particular value and try to make the standardized value as more than 3. Okay, try doing that, you'll get an idea what's happening. All right, but this one is very interesting, that standard deviation of the normalized values are somewhere between I mean the standard deviation of scaled values is 1. This is something that I am finding very how will I prove that part? Okay, so let me go back here. Right, what will be the mean of this? Okay, probably I'll do it in my own time. Great. So standard scalar class we use for this, and now using the standard scaling, we can quickly bring the values to between, reasonably within a very reasonable range, probably from 3 to -3 kind of range. All right. Now let's go back to the original example. Okay, so here we are computing the mean first, and then we are computing the 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 here we basically computing the standard values here, right? So we are scaling these values and so on, right? So here we've computed the standard deviation, we have computed the mean, we are subtracting each value with the mean and dividing by the standard deviation and so on. This is how the scaling works. For each feature we are doing it separately, and we are getting the scaled value. All right, so what kind of scaling is this? Is it a normalization or standardization? Is it min-max or is it standardization? Yes, just to check if you're awake. Yes, that's right. It is standardization. I mean, I keep using normalization interchangeably. Therefore, let's just keep min-max and standardization. Okay. What is the module available in this? There is something called standard scaler that we have used in past, and we'll be using that. All right. So moving ahead, and so all we need to do is pretty simple. All we need to do is we import the standard scaler from pre-processing package, and after that we initialize the standard scaler, and we call fit and transform in a single shot. If we call fit on the standard scaler first, it's going to compute the standard deviation and other values. And when we say transform, it's going to actually do this step. So that's an interesting part. So even the standard scaler is kind of a machine learning one. So here, when we say fit, it's going to compute the mean and standard deviation. And when we say transform, then it's going to apply this formula. All right. So that's what it is doing in this step. All right. So again, this was a quick review of what we did earlier. Now, so now we can plot the region boundary after standard scaling, and this is how it looks. Okay. So you can see the lane size, the street is not very thin or skewed. It is basically wide after data has been scaled, because this data which was varying from 20 to 80 is now varying from minus 1.5 to close to 1.5, right? And here this value that was varying earlier from 0 to 2, I think, right? Now it is close to, say, minus 1.8 to 1. All right. Deepak's point is, which class did we use for SVM? We're going to talk about it. We haven't used it any. We've just drawn it for this, just drawn the line. Though here is what we have quickly used just for plotting right now, SVM CLF. You can take a look in the notebook. We must have done it there. And just right now, we want to talk about that before we feed the data to SVM, we need to scale it. Okay, and why we need to scale it is the reason is very clear, right? In general, most of the algorithms, whether neural networks, whether SVM, whether the normal regression. So in general, the thumb rule of most of the things is that we have regression, the linear regression, where we try to draw the line and fit it. That's one technique. The second technique is SVM, whereby we come up with this kind of street which we fit it. And the third thing that we do is the descent trees, in which we split the data into buckets. And the fourth thing that we do is the neural networks, right? Those are the four main ways of solving these solving most of the machine learning problems. So those are four you can say that four techniques, right? While the techniques like gradient descent or something is, these are very generalized techniques. They basically help us in individual way, whether it's logistic regression, whether it's neural networks, whether other parts, we use the gradient descent, right? while but while we don't use the gradient descent in case of SVM or let's say descent trees, but we use gradient descent in case of regression, as well as we use the gradient descent in the neural networks. All right. So, and a gradient descent could be also used in many other scenarios, wherever you have some objective function and you want to figure out certain values. Okay. Even in non-machine learning problems, we use the gradient descent. All right. And so So generally, the general part of machine learning models is coming up with an objective function, and other is finding the optimum value, that optimization technique to find the optimum value. Therefore, gradient descent is called an optimizer. Okay, we could actually as well iterate over all the data and figure out the outcome, or we could use a mathematics. We could use mathematics to right away calculate the values instead of iterating, right? And before the iteration techniques came into play, we generally use the mathematical equations like SVM, or we use the normal equation the way we did earlier, the basically finding the differentiation and equating it to zero, computing values. That was the earlier norm. But soon enough, the computing and the mathematics overlapped, and the techniques like gradient descent and other other iteration way of doing things became more popular, right? If you look at what we do in case of grid search or random search, what we do in those cases, we are basically iterating, right? So the computing and the mathematical technique overlapped, and uh, earlier the mathematical techniques were more popular because the computing techniques weren't working because computers were not powerful. Today, since the computers are powerful, the computer techniques, the iteration techniques are significant, and iteration techniques are part of the core algorithm, and it is possible to do iteration. All right. Good question. So let me just answer Deepak's question. Do we use HDD classifier or logistic regression for classification? Yes. In HDD classifier, where we specify we are using logistic regression. Underneath, it uses that, and the way we specify that is by the way of defining that objective function in the arguments. All right. Okay, so we can change the objective function, and by default it uses the logistic that objective function. Okay. All right, can you show us the code? Yeah, let me probably, it's a good question. So let me see if I can uh let me take it to my notebook. Probably what I'll do is I'll just post this question myself on the forum, or you post this question on the forum and I'll try to answer in more details. It's an interesting question. And all right. So question is, do we use STD or logic? Oh, okay. Question is, do we use SDD classifier or logistic regression for classification? Good question. Let me go back. This one that I can clarify this right now. Okay, so logistic regression did not provide us any optimizer per se. It only provided a formulation of objective function, right? Logistic regression provided us with a formulation of objective function, right? Or you can say like cost function. The cost function was yi log y plus 1 minus y log of something, correct? So while the while the logistic regression that we studied only provided us the cost function, when we do optimize that cost function, we use standard the same the gradient descent technique. We could use batch, we could use stochastic, or you could use something else. But stochastic generally is considered better because we don't get stuck with the local minima, and it's pretty fast. All right. I hope that clears the question. No. Okay. Okay. Code wise is still the confusion. So do you mean that should I just take a look at the implementation of RGD classifier along with that? And okay. Okay, so yes, actually most of it is actually open sourced. So just the whole PyPy thing, the scikit-learn is written in something called PyPy. PyPy is a optimized version of Python, and yes, that's a good way to solve things. You can take a look at the code of SGD classifier sklan. All right. Here it should provide you with, you can see that in the SGD classifier, we can use hinge, which essentially would try to maximize the street. Okay. And yes, moving ahead, have they mentioned the code line? All right, let me just see if I could just quickly show you the code. No, yes. Okay, so this is the base SGD. Okay, all right. Here there are validations going on. Okay, and all right. So this is preparing data. That's okay. So fit binary is one thing, and then fit binary will be used for more using OVA probably. This is the base SGD classifier. Okay. All right. This is the documentation that we were just reading. It's coming from here, the code, right? That the documentation we just read. All right. All right. Let me answer your question. Okay. So yeah, question is how the all right. A question from Deepak is that do we provide logistic regression in solver parameters? That's the uh, question. So by default, that the one that we were just using. Okay. So the question is, the by default, does it pick the logistic regression or does it pick something else? Right? Is that your question? Okay. So this is where the loss function, if we provide as log, it gives the logistic regression. Okay. That's what I was trying to look for. Okay. So as I said that the logistic regression basically provided us a way of objective function. Okay. That's the one that it provided. So in case you provide hinge basically means we're going to use the SVM way, meaning it's going to try to find out that street that gives us the the maximum margin. Okay, if you put explicitly that log is going to give a logistic regression and so on. Okay, so this is a regularization penalty. This is the loss. What loss are we doing? All right, this is a good question. Thank you, Deepak. I think this was useful for everyone. So basically, the SDD classifier basically is that stochastic gradient descent. It's going to try to minimize the loss by the way of, you know, using the gradient descent technique. Okay. And the loss could be based on logistic regression, using mean squared error, using a hinge loss. It could be something else. Okay, it could be something else. It could be the squared loss. It could be it- the squared hinge. There are so many of other error functions that you can see. Okay, so SVM is one about finding the street. Other, SVM usually doesn't use STD classifier. This is another part that I would like to talk about. So SGD, sorry, the SVM has two parts. One is this objective function called coming up with the widest possible street, right? And the second part that is part of the SVM is the technique it uses. Under the hood, SVM by default does not use the gradient descent. All right. All right. So let's move ahead and okay. Now, okay. So this is what we have, and let's move ahead. So before scaling and after scaling, that's the story. And now, so linear SVM are very sensitive to scaling, and we should scale either using normalization, min-max, or using the standard scaler. Now, you can clearly see the difference. Okay, all right. Now let's just run it. Probably. Okay, so great, great. Let it open, and if you have questions, just let me know. And so what we're going to talk about is the soft margin versus hard margin classification. So hard margin basically strictly imposed that all the instances should be off the street and on a particular side of the region boundary. Issues it works only if the data is linearly separable and quite sensitive to the outliers. Okay. Okay. So let me just start running it. The standard part. So I hope this code is clear to everybody, the one that we're talking about. So we are importing the matplotlib pyplot, which is required for the plotting. Then we are picking up here two features, and X and the target. And here we are basically converting three classes into two classes. And here we are using SVM classifier for now. And then here we've created a function called plot SVC descent boundary. And here. Okay, so this is how we have done it. So going through it, moving ahead. So here there's a petal length and petal width and so on. So this is how it looks like. Okay, now the demonstration of SVM sensitivity, we are doing it here. Not much required, just you know, and and here we are showing how to compute the scaling, and then we are, yeah. So you can see this is after scaling, and earlier it was without scaling, right? So you can compare. Also, those who are thinking of, let's say, finding the standard deviation, try, how should I say? So try experimenting with the data, right? So let's say this is your NumPy array, right? And okay, so we are computing mean. Okay, just pick this one. Let's say this is our data and this is our NumPy array, and we are saying 10, 20, 1, 200, 2000, and 3000, or let's say 3. Okay, and we are saying we are first computing the data minus the mean of data, right? And we're dividing with standard deviation of the data, right? So you can see that this one, 2000, is actually 2. Okay, has become 2000 has become 2, and let's say even in this case, you can see in this case the standard deviation of this value is how much? It's actually 2. Okay, and no matter how much I'm increasing, it's not letting me go beyond some value. Okay, it's not going beyond 2, right? All right, one is minus 3000, and this is really huge value. This one is 0.5, and this one is still 2. Okay, the reason is that the standard deviation of this data is actually not letting it go beyond. So the moment we increase any of the values, right, suddenly the standard deviation also rises, and therefore it brings down the outliers. Okay, so you can try this out, and that'll give you an idea about why standard deviation is forcing it to this. Okay, and also try to do the min max and see how it goes, right? How do you do the min max? Data dot min, does it work? All right, there's something wrong. Never mind. So try this out, and probably that'll give you a good idea. Probably the number is so huge, min max did not really work. All right. So that was our quick understanding of scaling. Now let's go back to understanding the soft margin, hard margin. All right. So we're going to talk about hard margin and soft margin. Hard margin is basically strict that the every data point should be off the street, and the data point must be on the correct side of the decision boundary, right? So working on it works only if the data is really separable and linearly separable. It's quite sensitive to the outliers. Okay, so is it possible to use SVM hard margin classification? So can we put a hard margin in this kind of data? No, right? Because no matter how we fit the street, we are going to have margins. We are going to have outliers, or we're going to have violations. Now, if the if some a classifier is not accommodating to the outliers, it won't work, right? And same is the case with hard margin classification, because it's not really possible to say yes or no in this case, because there are some outliers. So we'll have to accommodate the outliers specifically in this kind of model, right? All right. Now, is it possible to classify this using SVM hard margin? Again, the answer is no. Yes. The answer is yes, but there's a huge problem, and that problem is, yes, the problem is, it is definitely, I mean, we can try to create the SVM hard margin classifier, but the problem is, this outlier is the problem, because what's happening is, because of this outlier, suddenly the margin that was supposed to be like this, the big street should be here. Instead of that, we're fitting a tiny thin street here, very tiny thin street. We should be ideally fitting a big street here, right? So whatever model we come up with, it should be accommodating to the outlier instead of yes or no, uh, instead of saying our way or the highway, we should accommodate the outliers, right? That's where hard margin classification doesn't work. Okay, that's where the soft margin classification comes into play. So in case we can't fit a street into the data, we say that it's not going to work. Instead of saying, okay, let there be error, and let's figure out a way of minimizing error, right? So that's soft margin, is that let's figure out how to how to minimize the error. Okay, instead of saying we can't fit a street into this because there is one outlier. In case of soft margin, we basically try as much as possible and accommodate outliers, in the sense that because of outliers, yes, we have error, but uh, we are not saying that we can't really classify just because there is one outlier. Okay, so soft margin classification is keeping a balance between keeping the street as wide as possible, limiting the margin violation, and the margin violations are regulated by using a parameter called C. Okay, so we have petal length and petal width. This is petal width and this is petal length, and we are trying to fit a street accommodating these margin violations. So you can see that this has gotten into the boundary, this has gotten into boundary, this has crossed the boundary, and so on. So it takes we basically trying to do is, we are trying to keep the error function such that the we are keeping the street as wide as possible, we're limiting the margin violations, and we basically doing a balancing act with the regularized the parameter called C. Okay, so the balance can be regulated in scikit-learn using C parameter. If so, basically we can see that in case the street is tiny thin, the violations will be higher, right? Violation will be lower if the street is tiny. If the street is wider, violations will be higher. If the street is tiny, very narrow, if the street is narrow, there will be less violations, right? If the street is wider, there will be more violations. right? So basically, there's a balancing act. On one hand, we want to keep the street wider. On the other hand, we want to keep the violations lower, right? In case we want to express our interest that we are interested more in the wider street than the violations, right? Then we can decrease C. If we are interested in narrower street, and violations are not something that we can tolerate. In that case, we would like to go with C, right? So though what will happen here is that in this case, if the street is narrow, the model will not generalize so well. If the street is wider, the model will not generalize, will generalize better, correct? If the street is narrower, the generalization is lower. If the street is wider, the generalization is more. Correct? Now, this is the important part. Why? Because in one case, we are reducing the error. In the other case, we are improving our model generalization, right? So what happens is generally we can't let go of either of them, and we should not, right? We should not let go of either of them. Instead, we basically tune it. We say that for us, the margin violations are a little bit more important. I mean, we should not have margin violations. So we will put C as 100. Okay. Remember our discussion on the precision and recall. Let's say in the similar way, in case we cannot tolerate the violations at all, in those cases we will basically keep increasing C in order to meet our requirement of classification. Okay, so C is basically what do you call it, the hyperparameter. So we come up with the C which satisfies our requirement with respect to the precision or recall, and the the kernel, we'll talk about kernel later, but for now understand that part, that though what we want to do is we want to come up with the naturally the way SVM regression works is that even if you give a bad value for C, you are going to get wide enough street with smallest possible violations, right? But in case you want to express our interest in saying that, hey, we can't tolerate the margin violations, in that case we can increase the value of C. Okay, I hope this is clear to all. A question from Deepak: a specific case where we must use SVM because still some companies are using it. Okay, that could be one reason, but uh, in some cases SVM performs really well. SVM, when you are okay, so it's a hard call again. It's a hard call again. Generally, what people do is they look at their problem statement and look at the time taken to train it. SVMs are very quick to train. They don't take too much time to train, and as compared to neural network or decision trees, they are really quick to train, and their predictions are also pretty good. Okay, the predictions are also pretty good, and but prediction wise, people use neural networks more as compared to SVM. So like for example, when you are building larger models, right? Larger models. So let's say you require I'll give you a practical use case where people use it. I mean, where I used it last time. Okay. Let's take the case of FaceNet model from Google, right? So there is this model which is basically converting face into features. Features means it's basically list of numbers, 100 values. Now, the face type basically gives you that. Okay, FaceNet, the library from Google, gives you a list of numbers, right? Now, what to do with these list of numbers is up to us. Okay, we could, using these numbers, we basically converted face into features, and we could either label it like this particular list, this particular vector is Arun, this particular vector is Deepak, this particular vector is Gonzalo, Jay, or Prashant. So what we do in this case is that we use the SVM classification to classify a person as Arun or Deepak or Gonzalo, right? And since SVM does not require too much of data for training, as well as it does not require too much time, so SVM works pretty well on such data, specifically the data which is well processed and is more doesn't have too much of errors. Okay, in those cases, the SVM seems to work very, very well. All right, so that's where I used it last time, that let's say we have some photos of people and we would like to quickly say that this photo is Arun, this photo, in this photo there's Deepak, and so on. So the easiest way was first converting the photo into features using, say, a library by Google, which basically understands faces. So it converts the face into a list of features. Okay, and we call that feature embedding. Okay, and once we have, let's say, some records, let's say we took 10 photos of Varun, 10 photos of Deepak, and photos of each of you. And what we did there was that we asked Google to translate that into embedding. Now we got our X and Y. Using this, we could do the rest of classification. All right. So that's one use case. I've seen you people using it, and it seems to work pretty well. All right, we'll talk about it more, and you will get more idea. All right, but this is a very important question, and we should all ask ourselves such questions. Okay, so good. Moving ahead, and assume classification for iris dataset using C equals 1. So steps are load the iris data. Okay, and the one that we're going to do, load the iris data, model the SVM linear classifier with the training set. Okay, and we will be fitting it, and then we'll be testing using our sample data. For illustration, plot the descent boundary and the training samples. All right, now, so this is what we're going to do. Now, first we'll load the iris dataset. We will model the SVM linear classifier, and then we will test. Do you see anything missing in the above steps? Those 3 steps? Yes, there are multiple things missing. Go ahead. Yes? Oh, we forgot to take a break. All right, so let's take a break for 10 minutes. Break for 10 minutes. Hi everyone, I'm back. Should we start? All right. All right. So, question from Deepak is that do we have overfitting, underfitting, regularization concept applicable to classifiers? Yes, of course. The 3 things basically. Good question. Good question. I think almost everything that wherever there is a prediction involved or there are models involved, we do have that overfitting, underfitting. All right. And the interesting part is that the mathematical functions like the one where, how should I say, the anything that does a prediction, there are chances that it is either biased or it does the memorization. Okay, so overfitting, underfitting is a universal concept. You will see overfitting, underfitting in even decision trees, in neural networks, in SVM also, I think. Let me just see. I don't think that we have too many regularization parameters. We do have C, which we fine tune, and using C, we basically come up with thin. If you take a look at it closely, thinner street is like overfitting, and a very wider street is the underfitting, right? If you look at it from strictly from underfitting overfitting perspective. So yes, whether classification, regression, in everything we have the idea of overfitting, underfitting. Even in the logistic regression, we do have the underfitting, overfitting applicable in as such. Similarly, when we talk about decision trees, we will see that if the tree has a huge depth, it starts memorizing more. And we saw even in the end-to-end project where we were doing regression. In that case, the trees actually memorized entire thing, right? So we do have the underfitting overfitting concept in both classification and regression, as well as in all kinds of models. Okay, in all kinds of models we have that. And like decision trees are mostly for the classification, but they can be used for regression. But in the classification, you will notice that decision trees, basically the new models like XGBoost, the first thing that they fine tuned is the overfitting. That's how they build the entire algorithms. We'll talk about it very soon. Wonderful. So moving ahead. So I hope this question was useful to all. And great, great. Keep these kind of question marks on things because that's how you will learn and you will develop your own model of things instead of memorizing what we are learning in the class. All right. So okay. So great, great. Moving ahead. So um, so yes. I was asking a question that what is it that we are missing? Yes, thank you, Deepak. Basically, converting target data set to multiple label classes. Okay, that is one thing that we're missing, and scaling. Great, great. So yes, and also we might have to split the data set if we don't have a separate sample data set, right? So that's what we have done here. Let's just run it. Yeah, we're done it. Okay, moving ahead. So let's do the SVM classification for iris data using C equals 1. So all we need to do is for now, we are just using this class called linear SVC. Linear SVC, and we are loading the iris data set. There's a function called load iris. And using that, we are loading iris, and we have capital X, and we have petal length and petal width, and we have the iris targets and so on. Okay, so all right. Then we are pipelining things. We are basically pipelining this scalar and linear SVC and so on. And then we are testing using the sample data. Okay, we are testing using the sample data like this, predicting. All right, now we are going to plot the descent boundary along with the, okay, so here, let me go back here. This part we have already talked about, moving ahead. Okay, all right, so here we have created the pipeline. What's wrong with this? Did we miss some things? Okay, what is happening here? Anybody? So we are saying, okay, standard scalar. This one is an tuple object does not support item assignment. Okay, why is it so? Anybody? So it says that okay, so let me just see what is the meaning of this part. So this is basically a pipeline. And what is it that we're passing to it? We're passing X and we are passing Y, right? So that is one thing that we're passing here. And when we say fit, okay, all right. So we have standard scalar. This is correct. And we have SVMCLF1. Okay. So when we are calling this, it's calling the self.fit. Then internally, it's calling the self.steps. And we are putting the name and fitted this, correct? And it says that the tuple object does not support the item assignment. All right, why would it happen this way? All right, is there a change in library? This is all okay. And if I just say CLF fit, this should work, right? If I say this dot fit, right, this has worked, but this one is probably there is something wrong with the pipeline. Okay, if I comment out this part in the pipeline, let's say the second part, does it still work? Yes, it does work. Now if I comment out the first part, does it still work? No, it does not work. So okay, so here it's not letting us do the, okay, so we could, can we just do the scalar dot fit transform and fit underscore transform, and we say X and Y, and we call it X underscore scaled. Right, this way. Is it a valid one? This is correct only, right? This is how we use it, or do we just need to pass X here? All right. All right. I think we could just let it be this way. We could define the scalar. Let's just leave that as such. Let- We'll just define something of our own right now, and then we'll see if we need to. Okay, so we just did a bit of change. Probably there is something wrong with the way we are using scalar. Yeah, y should not be the ideally we should not be how should I say is we should not be using the scaling on y. We should be scaling only on x. Okay. All right. So probably this fit transform anyway, the standard scalar dot fit transform anyway ignores the y part, I think. Okay, because scalar was supposed to be used in the pipeline, and in the pipeline you will get both x and y, and therefore probably it will be ignoring the second part anyway. Okay, and all right. So what did we do? Let's just say svmclf. Okay, for now I'll just keep the same name in my example, the one that we are using. Okay, here is we. All right, this one we are going to ignore for now and let it be the way it is. Commenting out, moving ahead. So we have the answer. All right. So what we did was we undid the pipeline. Let me make a note of it. Test the pipeline code. Let me just make a note for myself. Okay. And yes. Sure, sure. I'll just give you a copy of these. Okay. All right. So what we did was we basically here, let me go back here. What we have done is we have undid the pipeline. First of all, there's something wrong with the pipeline. Second, first of all, we use the scalar to, sorry, we used the standard scalar to convert the raw data into scaled. And then we initialized the linear SVC, and then we did the fit. Now, once we have done the fit, we can start predicting, right? We can start predicting, right? So, yeah, that's so we did the training when we did we again here we could do the unscaling. Okay, and where are we? All right, so first of all we did we convert the convert to unscaled parameters. What we're trying to do is we are doing the illustration right now. We want to plot the distance boundary along with the training data. So first of all, we did the fitting and did the training, and after that we convert to the unscaled parameters. And how do we convert to unscaled parameters is that there is something called decision function. This one provides a decision function. Okay, so this one provides the, does it work like that? Missing one positional argument. Okay, it means that it needs some data, the array of data which will provide. Okay, so it requires the raw data to in order to give you the decision function. So what's happening here, that whatever classifier we have come up with, we are saying that this is a decision function. And in the decision function, we are putting the mean and mean divided by scale. So scalar provides you those two values. Using this mean divide by scale, we are asking the SVM, the decision function, and whatever is the okay decision function, and then we are finding the intercept, we are finding the coefficients, and then basically afterwards we are finding the support vectors. Okay, support vectors and so on. All right. So basically, all right. I think let me explain this as we go ahead. It's just too much right now to I mean define all of this part. So I'll describe it soon. Okay. So it's basically all right. Yeah, I think it's better to just for now. Let's just use it for illustration. I'll describe it in more details as we go ahead. A question from Deepak is, but we didn't do the scaling in logistic regression or any other algorithm. We did. We did in case of this. Unscaling, why we are doing the unscaling is because we want to illustrate back. Okay. We don't need to do unscaling. We don't need to do unscaling for our training, usual training work. Here we want to display on the screen the decision function specifically. Therefore, we wanted to do the unscaling because we want to display the actual values here. We want to display the actual values. Okay. And yes, good question. So basically that's the reason why we are trying to do that. We just want to demonstrate that if we use c equals 1 the way we have done it here, c equals 1, whatever C as this SVM comes into play, it gives us the decision boundary, this and this, and using that we can display it on the screen. And when the C is smaller, this is bigger. Okay, when the C is bigger, the street is narrower. Right? You can see the difference. So we can fine tune C. And even if you make mistake in C, it does not mean that it's taking the entire decision based on the C. C is just a parameter in which you express that, hey, we are looking for more accuracy than the better model. Okay, so if C is bigger, it means that we are looking for better accuracy. If C is smaller, we are looking for better model, as in more generalizable model, meaning wider street. Okay. You can see it clearly that in case you run the same example here and so on. So we used which model out of these? SGD, SVC, or linear SVC? Yes. We used linear SVC. Okay. If you go back here, we actually used the linear SVC. Right? You see that? All right. I'm just trying to figure out to what depth should we go with SVM. Okay. And we'll just describe few things and we can go back because SVM, I mean, I want to save that time for either the neural network or the decision trees, right? But nevertheless, we'll just cover the entire thing so that you have a good enough confidence about the subject. Okay. So what we just now discussed was the soft margin versus hard margin. And to kind of negotiate between the two, we use the regularization parameter called C. Okay, small c means bigger street, bigger c means smaller street. All right, so that's what we want to demonstrate here. And now the second part we want to discuss is the nonlinear SVM classification. So far we have just used the fit and did the predict. We did not really go into exactly what goes into SVM. All right, so the polynomial features plus standard scalar plus linear SVC, that's what we are going to do. So it's very simple, just like our normal regression, we are using the nonlinear SVM classification. Okay, so there are many data sets which cannot be linearly separable. Also, please note that right now we are just talking about classification. We'll go into regression very, very soon. So many data set cannot be separated by a straight line. And what to do in such cases is that we, as we did earlier, we came up with more features, right? We did as x squared, x cube, x4, and so on. That was what we did in case of linear regression, that we added polynomial features. And when you add polynomial features, it could give you a linearly separable data set. Let's take a look at it, right? Now imagine this is your data. As you are increasing x, right? As you are increasing x, the class is changing. So this is one feature. When the features value was -4, the class was a square. As the feature became -3, the class was still square, and then as we reached -2, it became triangle. Meaning, for a value of x1 as -2, class is triangle. For x, the value of x is -4, the class was rectangle, right? Similarly, when you can see that for x equals to 2, the class is triangle, and as you move ahead, again it is coming back to this. If there was none of these data points, these two extra data points, we could simply classify it using the straight line. Or this side of the data wasn't there, then we could have classified it using a straight line. But now the problem here is that this data cannot be separated by a straight line, or you can separate. Yeah, can we separate it using straight line? Yes, no, right? It's a very interesting part that here we're not able to separate it using straight line, correct? We cannot separate it using a straight line. Why? Because the data is not as simple as it looks, correct? So what we do in such cases is that we square it. So what we are doing is, this was our original value. For -4, the label was 1, -3, the label was 1, for -2, the label was 0, and so on. And as soon as we reach here, the label was again 1. So 1, 0, and then 1. Now, the moment we square it, now the values look like this. Now let's take a look at it. So when the data becomes squared, right? What happened was, when we squared for this one, right? Okay. So what we did was we added one more feature. We added one more feature, okay? And that feature is the square of x1. Earlier, there was no second feature. There was no second feature, and we had only one x1 feature, and you can say that the second feature was just a fixed value. We could not linearly separate it because there was one single feature, or even if there was another feature, let's say that feature had no impact at all, right? So imagine that, or that feature was basically not related here. Now we added one more feature. Now we put that feature on the y-axis and this on the x-axis. Now if we use these two features, then the data is more separable. So what we just learned was when we introduce a new feature, even if that is derived from the existing one, our data becomes linearly separable. So instead of coming up with a model which is a curve, we band our data, we introduce more features, right? That's what is the very important part of SVM, that we come up with more and more interesting features, and the technique to find the straight line remains same one, because that the technique is basically a geometry based technique whereby we find the extreme values and try to draw a line here, try to draw a line here, and that becomes our street, and so on. So while the technique of finding that street remains same, it remains same. The technique to the technique to solve the data which is non-linearly separable is by the way of introducing new features. The way we introduced new feature here, and we saw that the data was separable. In the same way, we learned that we could introduce many more features in order to make the data separable. Okay. Do we limit to square only, or we may go for cube also? Yes, yes, we do go for cube and so on. And we are going to learn few more techniques that we did earlier in order to do the. We will learn those techniques now in order to introduce new features. Okay, we're going to talk about those techniques very soon. All right. So we call that kernel. We come up with the features. We say that, okay, this is called kernel and so on. We are going to talk about that. All right. So we made the data linearly separable using this technique. And here, that's what we are trying to do. Okay, let's just, yeah, we'll see that what's wrong with that part. Yeah, this is the part we are talking about. Probably I have messed up my notebook. Is your notebook running fine? Were you able to run this scalar, this piped one? Okay, same error. I see. I see. Looks like I need to revisit it. Okay, probably I messed up in my last class and I committed it. Okay, right. I'll be committing that one. All right. So for now, let's just the more important part about the SVM is to knowing that using SVM, you can fit the street using this particular variable. You could fine tune the street versus the error, as in the generalization versus the error. And again, right? As I said told you that if the street is really wide, we call it heavily biased because the model is giving too much of error. And if the street is too narrow, it's going to work great on existing data, but when new data comes in, it won't be able to generalize that well, right? So those are the things that right? Because the moment the street becomes tiny and tiny, it'll start behaving like normal regression where we try to fit the line, and again we'll reach the same point. Okay, so you can see that in one way, the capital C parameter that we're passing to SVC class is kind of controlling the overfitting versus the underfitting, the bias versus the variance, right? So because if the okay, so quickly, if C is big, will it underfit or overfit? C is big, it is thin, overfit. If C is small, then it will. If C is small, then it will underfit. All right. All of you, please stay connected. In case I missed out some ideas, please, or if there is something which is not clear, please let me know. Because the only way we can learn is by the way of Q&A or by the way of examples. All right. So by the way of examples, doing things as well as Q&A, we essentially, that's the only way to learn, right? Because just like we teach machine learning models by the way of instances and examples, we ourselves can also only learn by the way of examples. All right. My mental model, I can't really feed to you as input. Okay. That's why the examples is the only way to learn. All right. So yeah, that's something I strongly believe in. All right, let's go ahead and feel free to ask questions because questions is the way whereby I get to know that something I'm not explained correctly. Arun, Deepak, Gonzalo, Jay, Prashant, Robert, Satyajit, and Sumit. So please feel free to ask at any point of time. Okay, so let's move ahead. Here you can see that we have tried to do the same thing and it's pretty clear, right? All right, so now we're going to do something really interesting one. Okay, so in order to generate data, we have things like Moon's dataset. Moon's dataset is an interesting thing which generates a lot of data sets by itself. Okay, it's a good example, and people use Moon's dataset as the test for the classification. All right, so it's a random data generator provided by sklearn, and it basically provides two features. It's good for single label, and it has single label and used for binary classification. All right, all you have to do is you have to say that make moons, and we tell it how many samples we want to create and what kind of noise do we want, and we provide a seed. So this is the data set that is generated, and along with that, it has also generated the labels. This is how it looks like. Okay, this is how the data set looks like when we plot it here. So it's a non-linear data set, so we have to come up with a very clever way of separating the data, right? Now, similarly, if we generate hundreds of samples, now it'll make more sense to you. And this is how it looks like. Okay, so we have to come up with something like this kind of model. This kind of model, which is actually a model which requires a little bit more work, right? It cannot be separated linearly, right? Okay, so let me just show you what I mean. This looks good. Okay, let's move ahead. So we are here. All right, so okay, so can I just do 200 samples? Yes, 200 looks like this. Okay, if I don't print, it'll make more sense. For now, let me just not print it. Okay, I'll just not print it and then see. how does the data looks in case of say 2000 and the noise being really tiny. Okay, so now you get what we are trying to do. If the noise is very low, then it looks like a really good, perfect moon, as in two moons. Okay, with zero noise, this is how it looks like. All right. So now to separate such kind of data with a straight line is almost impossible, right? Right. So we need to transform this data so that we can separate this with the with uh, with the with the linear classification, right? Now let me just put some noise and okay. So this is our moons that we want to separate. All right. So right now question is, how do we classify or separate the two moons using a straight line? Can we do that? Can we do it in some way? So this is the data. This is one class. This is another class, right? If we divide it like this, lots of classes are going to go this side, lots of triangles and lots of squares are going to be this side, right? And the model will be underfitting, correct? The model will be underfitting because it will be having lots of error even in the input data, training data, as well as test data, correct? So what should we do in order to come up with the come up with a model which separates the two? Anyone? Arun, Deepak, Gonzalo, Jay, Prashant, Robert, Sadaji, Sumit. I hope you are still with me, or you have gotten busy in your own work. Uh, all right. Are you still attending the class? Or you gone to sleep? All right. Yeah. So this is our data, and we want to separate it, right? We want to separate it with a straight line or something else, right? So what should we do? What should we do? Okay, a suggestion from Prashant is instead of x2, we can have a new feature x3. That's right. That's right. Maybe we multiply x2 with a certain value. Very good point. Very good point. We could do that. Okay. And when we remember that when we multiply x2 with something, then this also will move up, this also will move up, and this also will move up, right? As well as this. All these values will get multiplied. So if you multiply, what will happen, right? This will spread out, correct? So whatever was point minus 0.5, this will become 0.25, interesting, and so on, right? You should give it a try. That's a very interesting suggestion. Okay. So yes, we need to add more features, more polynomial features in order to come up with a classifier which can separate the two, right? So adding, let's just try adding. What does adding polynomial features means? That let's say we add polynomial feature of degree 2. So what's going to happen is we are going to add x1 square and x1 into x2 and x2 square. Notice that it is x1 multiplied by x2. Okay, so when we add polynomial features, all we are doing is we are saying that x1, x2 we have. Now what else can we do about it? We could do x1 square, we could do x2 square, and also we could multiply x1 and x2, right? Now, of course, we can also divide, right? Okay. But for polynomial features, this is what happens. If we were using the polynomial of degree 2, polynomial features of degree 2, we'll be introducing more columns. We'll be saying x1 square, x1 cube. and x1 into x2 square, and x2 into x1 square, and x2 cube, like that, right? So adding polynomial features, let's consider an example here. When we add more features, then we get right. So let's say we did make moons and we got 2 samples, and we added polynomial features of degree 3, and then we did fit transform, and then we printed. So here all we are doing is we are adding more and more features. So when we added the polynomial degree 2, notice this, we are saying the polynomial of degree 3 here. Notice that there is a polynomial of degree 3. How many columns are going to be in X? In X, how many columns are going to be? 2 columns, right? So it has 2 columns, 2 instances. When I say make moons here, make moons, sample is 2, we got these 2 records. This is 1 record, this is another record. 1 belongs to the first class, 0 belongs to the second class. Okay? Right? So here we are saying x cube. X cube means we are adding the polynomial features of degree 3. So what we do is, okay, let's start here. So first one is here we are saying 0.08. That's the first one. Second one is 0.58. The third one is 8 cube. This is 8 cube or something else. Okay, and so on. So we do 8 cube, then 0.08 cube, and then we say 0.08 square. Probably is this 0.58 cube? Is it 0.58 cube? 0.05. So this is, let's say, x1 cube, x2 cube, x1 square, x2 square, x1, and so on. So this way, x1, x2, and so on. So this way, x1 square and x2 square also will be there. So all the lower degree as well, up to 3 degree, is included here. Okay, is included in this. All right. So what's happening is we are adding the polynomial features of degree 3, and we are using that polynomial features with doing fit transform. So it's transforming capital X into x1. Okay, so this is what's happening. Same is in the second case. We're adding so many features. So suddenly from 2, we got so many columns, right? So all this step can be performed in a single iteration using a pipeline, and this is what we've done here. I hope this will work this time. Oh, again, the same problem. Probably there's something has upgraded. Okay, something has upgraded. Okay, so what should we do? Should we translate, put it in separate one? I think we can do that. We could do that. Okay, so all right. For now, should we just? I'm just taking it apart, and I'll check out my code later. Okay. For now, let's just keep it this way. All right. So I'll just give it poly features. Okay, and we'll say we are introducing the polynomial features. Right here, we are saying x equals x, x equals poly features of x. Okay, and of course, scaling we need. So I'm going to say standard scalar. All right, and capital X equals ss dot fit transform. Okay, so I think this should be good enough. And the polynomial feature that we're talking about here, let it be like this. Perfect. So I'm going to turn it off. All right, let me just turn it off like this. Okay, let's just go up. It says that I made some mistake here. It says polynomial feature object is not callable. Okay, so we are saying PALF dot fit transform. Now what happened to this? X has two features per sample expecting 10. Okay, so what's wrong with it? We are saying fit transform. Let's say we call it X underscore P. We are feeding this here and we call it XPS, which is scaled, and we are fitting in here. And then, yep, X has two features per sample, expecting 10. Okay, so what's wrong with it? XPS. What's wrong with this? Anybody? Here, what's happening is we are asking the decision function and we are reshaping it. That's okay. And then we are saying polynomial. Okay. And which part is it 3? Before we are using capital X while plotting. Okay, so yes, you are right. So yes, you are right. So here is the problem probably. What's happening is here there is something like that. Okay, so looks like we have done something wrong here. X1 dot reshape. This is all okay, and we are doing that. All right. Yeah, this needs to be revisited. Probably there are a few things that have changed. Okay, let me, before plotting here, let me just comment out everything and let's just take a look at XPS. Okay, we say, or we'll just let it run first. Okay, okay, so far so good. And when we say print XPS, okay, so XPS has how many? What's the length of XPS? Or we can just say XPS dot shape, XPS dot shape. So it has 100 rows and 10 columns. That's good. And that means that our model till this point is perfect. At this point, you can see that we had two features and we introduced probably 8 more. That becomes total 10 features. And here we are defining this function. Let's just do that part. Okay. Now, when we are doing the plot predictions, what's happening inside is that there is a classifier that we are passing, and then there we are passing the axes, right? So these axes are what? These axes are these values. I see. I see. So probably somewhere I see. So probably we are using the classifier, the one that we are passing earlier. Okay, okay, I got it. I got it. So what's happening right now is that we are what we're trying to do is we are here trying to plot the data set as well as this. Okay, so yep. So what's happening right now is that the data set that we're passing here, these axes is okay. We generate x0, x1, unravel, and here we are using the predict. Okay, which means that we'll have to introduce this transformation here as well. Correct? Here as well. So for now, I can just define my transformation. Okay, this is my transformation, and whatever is the x that we are passing, it's going to translate that into something. Let me just do it quickly. I hope that's okay with everybody. Let me just define this simple function and we'll just return. Okay, we'll see to that later. Right now, we are just taking capital X. We are translating this into XP, and then we are saying standard scalar and transforming it. Okay, so and then finally, this is standard scalar, and again, we are okay. So let me just put it this way. I know that it sounds crazy, but for whatever reason, this has stopped working. Okay, all right. Now, I've defined this transformation function of my own, and it should now work probably. What's happening right now here is that we have defined this classification, and whatever classifier we are passing here, instead of using that to predict, what we will do is we will call our XF function, right? XF function with this classifier, and whatever is the dataset X1 that we got here, and then we are going to use this to do the prediction. Oh, we can't do that. Okay, so just give me a second. What can be done? Okay. All right, let's just keep it aside. Okay, let me just do that. Except what was our input data set, which we needed to transform? We needed to transform X. X became XPS, yeah, like that. And that's our transformation. So we do the transformation of this X1 in the same way. So we say X1 equals XF, and then we do the transformation, and then we do the prediction using the same classifier, and that's it. So we are saying plot predictions, we are passing the polynomial classification, and then we are passing these values. And here what's happening is we are picking up these values, okay, and then we're creating a mesh grid, and then we are basically concatenating that, and using this we are doing the fit transform. Okay, we are using the fit transform to do that. This is correct. Okay, all right. And then we are saying CLF dot predict on X1. This is right. Ouch. There's still something wrong over here. We are saying CLF dot decision function X, CLF dot decision function X. We just need to say 1. All right, so this is what we did. All right, let me just give you this. Whatever changes we made, looks like I can't copy paste this just like that. Okay, let me just delete the comments, and probably then it'll be small. Okay, so I'm just giving you what I've just made changes, and so that we all are on the same page. Okay, so great. So try running this. So now we can see that there are these two features, this and that, and we are able to create the nonlinear decision boundaries, right? Okay, this is what it is supposed to be doing. Okay, and I'm hoping that I see the data set is not yet what do you say? The data set is on different scale altogether. Okay, And that's why we have, now it makes sense. All right. Try putting this as well before plt dot show. Okay. So this is what we get. There's a little bit of difference, but yeah. So what has happened here is this is the decision boundary that has come up after training it on so many features. We got this decision boundary. We got this decision boundary. This decision boundary is a result of creating the decision boundary in other dimensions, other against other features. All right, because there are 10 different features, so we drew the decision boundary in all those 10 features, and the result is that as a result, when we were when we created the classifier, probably in against other feature, those are straight lines. Those are straight lines. Those are straight lines, and when you are plotting those, plotting against one another, then the decision boundary that comes out to be is a nonlinear. The decision boundary that comes out to be nonlinear. So with the linear regression or with the linear classifier like SVM, when we introduce the polynomial features, we are able to come up with this kind of nonlinear boundary, right? Is it clear to everyone? So all we needed to do was instead of using the two features, we used many features. And as a result, when if you think about it, if you draw the other features against x1 and x2, and then see the classifier's behavior, there'll be straight lines. And when you ask those classifiers for each data points, that for this, what will be, whether this is the recent boundary or this is, then the outcome is a non-linear recent boundary, right? So with SVM, we were able to achieve a lot. All right. So that's pretty much for today. All right. Bye bye. Have a good day.